Okay everyone, this is Dr. Graham and this is my first attempt to record a lecture that I'm not giving to an actual class, so hopefully it goes okay. So this is what we're moving into now. We're moving into working with ANOVA. So this is the introduction to analysis of variance. And where does that term ANOVA come from? Well, it comes from those first two words of analysis, or first two letters, the O of and the VA of variance. So that's where ANOVA comes from. Okay. So what is it? ANOVA is a technique that's used to test differences between sample means, which is a lot like what we've already been doing with t-tests. However, it can be used to test whether any number of means differ. So far with t-tests, we've only been working with two different means at a time. With a one sample, we had one mean that we compared to a population mean. And in paired samples and independent samples, we've had two different means that we were comparing to each other. It can also be used to look at the interactive effects of two or more variables. So for example, if we have more than one independent variable, if we think more than one variable has an effect on some outcome, then we can look at how those two or more variables interact in terms of having that effect on the outcome. And the way it does this is it compares the variability within our groups to the variability between our groups. And if the between groups variability is a lot bigger than our within groups variability, then we can make claims about there being a significant difference between our mean. So here we see three different population distributions. So there's the one in black, green, and pinkish purple. Right? So we have mean number 1, number 2, and number 3. So these curves here show one particular kind of scenario where the alternative hypothesis is true. And the alternative hypothesis being that the means are not the same. There are, of course, other alternative hypotheses. Maybe the black curve and the green curve are the same, but only the pink curve is different. Maybe the green curve and the pink curve are the same and the black curve is different. Maybe they're more spread out, maybe they're closer together. Maybe the pink one is just really far on the right hand side, but the black and the green are close. Right, so there's all sorts of different scenarios where the alternative hypothesis would be true. And that alternative hypothesis being that at least one of the means is different from the others. So with one-way ANOVA, and one way just meaning that we have one independent variable, what we're actually testing in terms of the null hypothesis is whether the three means, or three or more, right, means are different or if they're the same. So the null hypothesis would be that all of our means are the same. In this case, mean 1 is the same as mean 2, which is equal to mean 3, which is the same as mean 1. Okay. So in our null hypothesis would always be all the means are the same, and our alternative hypothesis would be at least one of the means is not the same. So there could be two that are the same, but if at least one of them is not equal to the others, then our null hypothesis is false. So the assumptions for ANOVA include the independence of observations. So this just means knowing that one score in an experimental group tells us nothing about another score, right? So one person's score on a test doesn't influence somebody else's score on a test. We also assume that we're using some form of randomization, that participants are selected at random and they're randomly assigned to be in different groups. Now this one, you remember we talked about very recently when we were talking about t-tests, that we assume that the scores in each group are normally distributed. And we also talked about, when we talked about independent samples t-tests, we talked about the homogeneity of variance assumption. So variance, of course, meaning kind of how spread out the data are, whether they're very close together or very far apart, right? So if we have, let's see if I can get this working, right? So we wouldn't want one to be like this, and then another group to be really spread out in comparison, right? So when we're talking homogeneity of variance, the homogeneity part means the same, And variance is referring to like the spread that we see, right? How much do the scores vary? Okay. So just like in independent samples t-test, in the one-way ANOVA, we have this assumption of the homogeneity of variance. We assume that the scores in each group have approximately the same variance. And in SPSS, this can be tested by selecting an option under the Options button in the ANOVA menu. So it is important to note that ANOVA is pretty robust with respect to violations of normality and homogeneity of variance. So what that means is ANOVA still works pretty well even when we have issues with normality and issues with homogeneity of variance. So if our data aren't really normally distributed, if we have maybe a bimodal or it's pretty skewed one way or the other, then ANOVA is still pretty good even in those cases. And remember that whole normality assumption thing, we're really working with sampling distributions, and thanks to the central limit theorem, this tends to check out anyway as long as we have enough people in our sample. And this homogeneity of variance one, even when our groups are, kind of different, so let's say that we have one that's maybe pretty tight and then another that's pretty wide, that would maybe be okay. What we really want to look out for in this case is when we have large inequalities in sample sizes, so one group has a very small sample versus another group has a very big sample size, and large heterogeneity of variance, right? And heterogeneity is just the opposite of homogeneity. It means that our variance is very different in our different groups. And of course, in ANOVA, we're dealing with more than two groups, so maybe we have that red group there, the green one here, and then we have this orange group that's really peaked, right? So if we have very different sample sizes in these different groups, and we have very big differences in variance, then that's when it tends to be an issue. So when we're talking about variability within groups and variability between groups, what makes up that variability? When we're talking about variability, we're just talking about why scores are different. Why do people get different scores on different things, or why do they have different outcomes? So when we're looking specifically within groups, we may get differences in scores due to individual differences, right? People are different from each other. There also may be errors of measurement. So think back to when we measured our fingers, and people may be measuring slightly differently. They may be using slightly different kind of rulers. So maybe they just read it wrong. So we have these two things that make up why we have variability within our particular group. Now, when we have between group variability, we still have individual differences and we still have errors of measurement. But on top of that, when we're looking between our different groups, that's when we're talking about treatment effects. So whatever is different between our groups, so group A and group B and group C, whatever it is that makes them different groups, that's what we would refer to as our treatment, right, or our condition. So in that case, on top of just individual differences and errors, we also have the effect of whatever that thing is that we're looking at, our treatment or our condition. So keep that in mind when we're talking about the kind of how we find F, the F ratio, because the F ratio is made up of these two components, the between group variability and the within group variability. So the logic of the one-way ANOVA is that we calculate two estimates of population variance. And again, variance just referring to that idea of variability and differences in scores. So the MS error is based on the variability within our groups, right? So that would be just individual differences and error. And this is independent of our null hypothesis. So remember, our null hypothesis was that if we have these three groups, right, and each of these has a mean, So our null hypothesis is that the mean of 1, so if this is 1, 2, and 3, that the mean of group 1 is equal to the mean of group 2, which is equal to the mean of group 3, right? That they're all equal. So if we're looking at the variability within groups, so that would be the variability only within this particular group, the variability only within the green group, right? And the variability only within the purple group. Well, if we're talking about only the variability inside each of these groups, that has nothing to do with whether they're the same or different from each other, right? So that's independent of this. We can't, if we only look inside of each group, then we can't test this because we're only looking inside. When we start talking about the variability between our groups, that means we're comparing the variability all the way across, right? So the variability between these two groups, like all the variability that's included in the whole segment. So that particular part is very much related to the null hypothesis, is dependent on the null hypothesis, right? Because if, let's see here. Well, let's just start over here. So let's say that our null hypothesis was true. Then curve 1 is the same as curve 2, is the same as curve 3, right? So in this case, our between groups variability and our within groups variability, it's the same thing because they're all right on top of each other. So it's only when these groups are different from each other, right, maybe even just a little bit different, that you see the variability that spans from one end to the other between the groups is bigger than just this variability, just this variability, just this variability. So within groups is independent of the null hypothesis. Between groups is what actually tells us information about the null hypothesis. If it's true, then our between groups variability will be the same as our within groups. If the null hypothesis is not true and there's any difference, then we expect our between groups variability to be bigger than the within group variability. Okay. Let's delete some of this stuff here. Okay. So here is our F ratio. So the F ratio is the between group variability. So keeping in mind that's the variability all the way across our three groups, or however many groups that we're talking about. So that's the between group variability. Versus the within group variability is the variability within each particular group, right? And we actually end up averaging that out. So that's the within. So we take this difference that goes all the way across and we divide it by the average of, these little differences. So if this difference all the way across is really big compared to the difference just within each one, then we get a really large F value. If it's not very big, then we get an F value that's pretty close to 1. And why is that the case? So let's say that they're all very much on top of each other. Then this between groups variability is going to be basically almost the same as the within groups variability, right? Much closer to the same thing. So we call this between groups variability, and abbreviation for it is MS group, and we'll talk a little bit about what that MS stands for. But remember this group part. So that group part, let's highlight that there. So that's because we're talking about the variability between our groups. This MS error, which corresponds to within variability, That's because we're talking about only within our group, right? And we said what accounts for the variability within a group? Well, it's both individual differences and it's just error, right? So what accounts for this variability here? Within groups, individual differences and error is what accounts for a variability within our group. And one thing to note here, when you see this MS group, MS error, MS simply stands for mean square. So it's short for the mean of the sums of squared deviations around the mean, which is the variance. Really, we're just referring to, is it group variance, variance across the groups, or is it error variance, variance that we see within our groups. So as I mentioned, if our between group variability and our within group variability are pretty similar, then that means that we're seeing something like this, right? That all of our groups, oops, that should be a different color. Let's start over. So our black group and our green group and our purple group, this would be the case where our between group variability, right, the variability across all three groups, is basically the same as the average variability within our groups. So if these two things, these two components that make up our ratio are similar, then we have no reason to reject the null hypothesis. The only reason that our between group variability and within group variability would be very similar is if our groups are all about the same, right? If they have the same mean and if they all just kind of fall on top of each other. So when our MS mean square groups is much bigger, that's what this is referring to, much bigger than our MS error, then that's when we see differences between our groups. And that's because we would see like in this case, our between group variability, our MS group, is pretty wide, versus if we were to average this little group variability, this variability, and this variability, then we would essentially come up with something that's like this width versus about this width, right, if we were to average these three together. So you can see that this one on top, the MS group, is much bigger, it's much wider than the MS error, right? So it's about 3 times as wide in this illustration. So when our MS group, our between group variability, is much bigger than our within group variability, then this means that the differences between our group means must have contributed to this particular between group variability. And in this case, we would reject the null hypothesis because our means of our groups are most definitely not the same. Okay. So how do we get F? I mean, we saw the equation for F, it's this in the blue, right? But how do we get MS group and how do we get MS error? So we need to identify how we calculate these things. Where do they come from? So in order to get MS group and MS error, we need to know SS group and SS error and the degrees of freedom that go along with each of those things, right? So what the heck are we talking about? What does SS stand for? So SS, we've talked about before. You have to go in the way back machine and go all the way back to week 2. And we talked about SS back in week 2. So to jog your memory a little bit, here's a slide from week 2. So remember, we started out talking about visualizations, then we started talking about central tendency, like means, medians, mode, and then we talked a lot about variability. And this is one of those slides from when we were talking about variability. And if you remember way back, feels like a long time ago now, we had like a list of numbers, and then we were trying to find like the average deviation. We started talking about what a deviation is, right? And so a deviation is simply, you know, one number minus the mean. That represents a deviation. Then we started adding them up, and we were trying to find the average deviation, and we found if you did that, it always added to 0. So we did something in order to get rid of all those negatives and positives so that it wouldn't add to 0. What we did was we squared all those numbers. So then we were finding the mean of all of our squared deviations, right? So for example, if we know our mean is 5 and we have the numbers 4, 3, 6, and 7, I'm just kind of hoping that those all add up to a mean of 5. Then the deviation of these would be, okay, 4 minus 5 is negative 1. 3 minus 5 is negative 2. This one, 6 minus 5 is positive 1. And here, 7 minus 5 is positive 2. If we added all those up, negative 1 plus negative 2 is negative 3, plus 1 is negative 2, plus 2 is 0, right? So that was pretty useless to us. So what we did instead was, well, let's just square all of these numbers. So hopefully this sounds vaguely familiar to you. And then when we added up all of these squared numbers, so 1 squared plus 2 squared plus 1 squared plus 2 squared, so 1 plus 4 plus is 5, so this ends up being like 10, right? And this was our SS. It was the sum of our squared deviations, the sum of squares. So hopefully that phrase sounds vaguely familiar, sum of squares. And that is exactly what we're talking about here when we're talking about SS. We're again talking about deviations from the mean and then squaring them and adding them up. So yes, it just stands again for sums of squares. So the sums of squares is the same one that we talked about when we were calculating standard deviations. And why is that the case? Well, because we're talking about variability. Remember, we said standard deviation is a measure of variability. It's the square root of the variance. And here again, we're comparing variability. We're comparing the variability across all of our groups, between groups, and then we're comparing that to the variability within our groups. So it makes sense that we're talking about variability and that we're talking about sums of squares again. They're very much related. So in addition to our sums of squares, for both across all of our groups, right, between group and within our groups, we also need to know the degrees of freedom associated with across our groups and within our groups. So to calculate our degrees of freedom, so before all we did was, like for t-tests, we did n minus 1. And that was our degrees of freedom, right? Slightly more complicated now. We're building on what we worked on before. So now we have 2 different degrees of freedom we're looking at for group and for error, so between and within. So here's our total. If we wanted to do the total degrees of freedom, it's the same as before, n minus 1. N is the total number of observations we have. Subtract 1 and we get our total DF. But you'll notice this in right here, this isn't total DF and this isn't total DF. So how do we get degrees of freedom for group and degrees of freedom for error? Well, for group, super easy. You take the number of groups that you have and you subtract 1. So like when we're talking about, okay, the black one versus the green one versus the purple one. Oops, let's get rid of that one. Here we go. How many groups is that? Well, that's 1, the black group, 2, the green group, 3, the purple group. So in this case, we would plug in, here is 3 minus 1. Our degrees of freedom for group is 2. So we take our sums of squared and divide by 2. Now here we see, this is the other thing we are looking for, right? So here's our degrees of freedom for group. This is our degrees of freedom for error. So to get this, we take degrees of freedom total here, right? Plug that in. Then we take our degrees of freedom for group, plug that in, and that's how we get degrees of freedom for error. So if we had, let's say we had a study where we had 30 individuals, 10 in each of 3 groups, right, with 3 groups. Well, then our DF total equals 30 minus 1 equals 29. Our DF group equals 3 minus 1 is equal to 2. So then our DF error is equal to 29 minus 2. It will be 27. Okay. So once we have added up, so we've taken all our deviations, we've squared them all, and we've summed them all, then we divide by our degrees of freedom for both our group and our error, then we can calculate our F ratio. Because that's just, so keeping in mind this top part is equal to SS group divided by DF group, and then over this bottom part, SS error divided by DF error. All right, so we're just plugging in. And at that point, we have an F value. We can plug in all the different numbers. We get one number, that's our F. Now, when an F value is calculated, we can refer to an F table, a lot like a Z table or like a T table. And I haven't posted one yet, but I am going to post one on Blackboard under additional resources, just so you can see what it looks like. It'll look vaguely familiar, sort of like a t-test, but not exactly. But like in the t-test, where we had to look like in the column and in the row, and one of them was our degrees of freedom, and then the other was like what, probably like what alpha level you wanted to use. Then F is going to be kind of similar to that, in that we're going to have to look at both the group degrees of freedom and the error degrees of freedom. And then usually you'll have one table that represents a critical value alpha of 0.05 and one that represents 0.01, because it's also a common measure or a common alpha value that is used like in the social sciences, health sciences, and so on. So I'll post up one of those just so you can see what it looks like. We're not actually going to be using it at all in this class because, like I said, with t-tables, people almost never actually use those. They don't calculate t by hand and go look it up. Don't calculate f by hand to go look it up. That's what we have computer programs for these days. So we will learn how to do it in SPSS, where it gives you the p-value. We don't have to calculate f ourselves by hand and then look up the p-value, because SPSS does that. But I do want you to at least have the exposure of seeing how or where these numbers are coming from. Right? Okay. So here's our F again, MS group over MS error. And just to reiterate what we've said before, if the between groups estimate of population variation is a lot larger than the within groups estimate, then our F value is going to be greater than 1. Right? If these two are the same, they're going to be about equal to 1. But if this one is bigger, meaning that our means are different, then it's going to be bigger than 1. So how much larger than 1 does our value have to be in order to decide that if there's a difference or not? That depends on the degrees of freedom. That's why in the F table, you have to look up degrees of freedom for the group and degrees of freedom for the error. So let's just run through an example here. So here's we have 3 groups. We have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? 1, 2, 3, 5, 6, 7. Yeah, 9 people in each of our 3 groups, right? So here, n equals 9. So all together, we have what, 27? Okay. So for this first group, if we were to add all of these numbers up and then divide by 9, we'd see that the mean is 6.3. Yeah, make that a little. There we go. For this second group, if we add up all 9, divide by 9, we'd see the mean is 4.3. And then for our last group, if we added them up and we divided by 9, we'd get a mean of 5.3. Now this variance is, if you think way back, so this is like our sum of squares, right? So if we were to take 3 minus 6.33, where'd that come from? That's the mean. And square whatever that is. Then we do the same thing for this one, minus 6.33, and square that up, minus 6.33, and square that one. And we do this for all of them, right? Just keep doing it. And then we add up whatever that comes to. And then we're starting to work with our variance, right? We're getting to sums of squares, and then from sums of squares, I can't remember the exact equation, I think we divide by n, and that would be our variance, right? So same thing here, except here we're minus 4.33, square that, minus 4.33, square that, and so on. We add them up and we divide by 9, then we would get a variance of 10. Same thing here, minus 5.33, square that, and so on. So this is where this variance of 10 is coming from. It's from taking our sums of squares divided by n. Okay? So let's just walk through this, and let's clean this up a bit first so we can just see what else is happening. Okay, so it's a little cleaner. Okay, so if we were to add up our means and divide by 3, we would get the grand mean, which is equal to 5.33. Here we see our number of groups is 3. And remember, if you think back to that other slide, k equals 3. So then that's related to our degrees of freedom for groups, right? And number of scores in each group, n equals 9. So the sampling variance, we take the group mean, so this, minus the grand mean, this, square it, and we do that for all 3, right? So we would take 6.33 minus 5.33, which is going to be 1, right? Squared is 1, divided by k minus 1. K is 3, so we divide by 2. So this is going to be 1 over, is that right? 6.33 minus 5.33 is 1 over 1. Oh, because we need to sum it up first. Duh. Because this one, 4.33 minus 5.33, here, I'm going to clean this up and do it over again. Okay. So, let me try to write a little bit neater. So we'll do the first one. 6.33 minus the grand mean squared. Okay, so this is 6.33 minus 5.33 is 1. Squared is 1. Here, 4.33 minus 5.33 is negative 1. But when you square it, it turns into what? Positive 1. And right here, 5.33 minus 5.33. So 5.33 minus 5.33 is 0. Square that, and we get 0. So this part, add up that part. 1 plus 1 plus 0 equals 2. Then, whoops, just delete this box so we can see more clearly. So that's the top, right? Then divided by k minus 1. Well, k is 3. 3 minus 1 is 2. So then the bottom is also 2. 2 divided by 2, and that's where this 1 comes from. Okay? So our two estimates of variance are our between groups variance is MS group, and we get that's n times our sampling variance. Sampling variance is what we calculated here. Okay. So 9 times 1 is 9. And then the average variance within our groups, well, we're talking about these. What's the average of 10 and 10 and 10? The average is 10, right? 10 plus 10 plus 10 divided by 3 is 10. So then we would take this one, between groups, MS group, divide by this one, MS error, and we see F equals 9 divided by 10, 0.9. It's pretty close to 1, right? Which is what we would said that we would get if the between groups variance was pretty similar to the within groups variance. Or in other words, when the null hypothesis is true and the three means are almost the same, right? Or relatively the same. So to do this, I'm not going to show it in SPSS right now, but when we're in class, we're going to go through it together. But you would go through the Analyze menu, then you go to General Linear Model, and select that we want to make a univariate model. You want to select the options to estimate effect size and do homogeneity tests. And remember, this homogeneity test, this is what we do to make sure that we're meeting that assumption of homogeneity of variance. So if you think back to our independent samples t-test when we had Levine's test, and that was that p-value that told you, do we read the top line or the bottom line of the t-table? Same idea. So here is the outcome of our Levine's test, and if let's see. So if P is greater than 0.05, then we meet the assumption. We're good to go. If P is less than 0.05, then that means that we have an issue with our with meeting our assumption of equality of variances. Okay, so we'll talk later about what to do if that happens. Then we get an output that shows our tests of between subjects effects. So this is like our between groups effects. Now in true SPSS style, they give you like 50 numbers when all you need are maybe 3 numbers. So where we really want to focus here is on this line right here. All right. So this is referring to the data from the previous example where we have the 3 groups. So we're looking at what's the effect of group. We see our degrees of freedom for our group. We can see our total and our error degrees of freedom. And then we can see here's where our MS group, our MS error, and then we get our F, which was 0.9, and then SPSS tells us that our p-value for this particular F value with our 3 groups and the number of participants we have is 0.420. So we have to ask ourselves, should we reject the null hypothesis or not? So thinking back to Snoop Dogg, if the p is lower than 0.05, then the home must go, then we reject the null hypothesis. Is 0.42 lower than 0.05? No, it's not. So we don't reject the null in this case. We would retain the null. Alright, so we'll keep it. Because we don't have sufficient evidence to reject our null hypothesis. Our means aren't far enough apart that we're confident saying that they have to come from different populations. Our between group variability is not so much more than our within group variability that we can say, nope, these are from different populations. So what does it look like if our alternative hypothesis is actually true and at least one of the groups is different from the others? So here we see, again, 3 groups. Now we have 3 different means, right? So our grand mean, 5.67, that's the mean of these 3 means. We still have 3 groups. We still have 9 in each group, right? So if we were to do like we did last time, where we did 8.33 minus 5.67 and squared it, and did the same thing for these 2, and we add those up, that gives us this top part. Okay. And then we would divide by 2. If we did that, we would get 6.33. Now to get MS group from that, this would be our N in each group, 9, times our sampling variance, and we would get 57 on top. Our variance, if you see, like right here, oh, that doesn't help. Right here, our variance is still the same as last time. It's only our means that changed, right? So our variance stays the same here. If we plug in 57 divided by 10, we get this time our F is 5.7. And if we were to go through SPSS, analyze general linear model to univariate, we see, okay, we meet Levine's test again, that's good. And here we're looking at our group. Here's our F of 5.7, and this time, whoops, oh, I can't go back. Sorry guys. Well, it was 0.009, so that time it was significant. We would reject the null hypothesis because 0.009 is less than 0.05. Sorry, I can't go backwards if I'm recording apparently. So let's do another example, or an actual example. So this is an example where we're studying the different treatments for Parkinson's disease. And a group of medical researchers are doing a double-blind between participants design. That means that it's different people in each of our groups. And we have 10 patients in each group. So we have 10 in this group, 10 in this group, 10 here, and 10 here. Double-blind means that neither the patients know which group they're in, and also the researchers don't know which group the patients are in when they're treating them. they have like some Excel file somewhere locked away that tells them so they can figure out later who is in which group. But when they're interacting with the patients, they don't actually know which group the patient is in. Okay. So our dependent variable here is that they are assigned a score from a physiotherapist, and the score represents the improvements that the physiotherapist has seen in their mobility measured after 6 weeks of treatment. So it's important to note that if a patient gets a negative score, that means that their mobility has actually gotten worse over the time period. Okay. The 4 groups that we're comparing are a new therapy control, right? Or sorry, no therapy. So no therapy whatsoever. So that's a control group. They're getting absolutely nothing. Then we have a placebo group, which is getting some sort of like sugar pill, something like that, right? Where it shouldn't have any effect, but they're getting just a nothing pill to see if even just thinking they're receiving treatment is going to have an effect. Then we have some sort of conventional therapy, what's usually used with the participants or the patients of Parkinson's, right? And then they have some new age therapy. Maybe they have something, I don't know, something with like crystals or essential oils or something that they think may have an effect, and they want to see, does this new age therapy help to treat Parkinson's disease? Okay. So we want to see all these different things. So here are our scores. We have the scores for the no therapy control group, for the placebo control group, the conventional therapy group, and the new age therapy group. And again, notice when there's a negative score, that means that their mobility has gone down. Oh, actually, now that I'm looking at these, I see that when I copy and pasted them, I didn't actually update the numbers, but trust that in the SPSS file that I used to do the outcomes for this example, I did change the numbers. So these numbers are not the right numbers. I will have to update these slides. So obviously, I did the same thing in every group. So ignore that. But in SPSS, assuming these were the right numbers here, right, each group's numbers were accurate, then in SPSS, you would enter those scores in one long column, right? So at the end of this one, we would go up to the next one, and then we would go up to the next one. Well, let's clean this up a little. So assuming that the numbers were all right. So we would start here, we would put all these in a column, then when we got to the end, we would just keep numbering down this one, keep numbering all in the same column, right? So you would have one long column with 40 numbers in it. Then next to that, you would have a second column, and in that second column, you would put next to each of these a 1 for being in this group, right? Then the next group, next to each of them, you would put 2, and that means they're in this group. These ones are all 3, right? And these are all group 4. So each number would have another number that represents which group it's in. So at the end, you have 2 columns. The first column is their actual score. The second column says which group they're in, if they're in group 1, group 2, group 3, and so on. Okay? So in SPSS, we go Analyze, General Linear Model to Univariate. This time I'm adding the tick box for descriptive statistics, so we get our means and standard deviations. And then here, this is just to show you, I'm going to show you a graph of the outcome. And so this is reference for you to be able to go back and see, how did I get that graph? Well, I went through graphs, through chart builders, bar chart, simple bar chart, and then it tells you what to put on which axis. And then in element properties, there's a special dialog box called that. You would tell it to display the error bars, and then click apply, and it'll add in 95% confidence interval bars. So this is what the outcome would look like. We get our descriptive statistics, which shows us the means and standard deviations for each of our 4 types of therapy or treatment. And then we get our Levine's test, right? So here, not significant, which is actually what we want in this case. That means there isn't significant difference in variability between our groups. Then we have a test of between subjects effects, and here this is no longer labeled group, it's labeled treatment because that's the name of our variable. We can see our F value, our significance, and then this right here, partial eta squared, that's our effect size in this case, right? And we're going to use these 2 numbers as our degrees of freedom. Okay, so we saw that there was a, remember P came out as 0.000. We don't write actually 0.000, we would write less than 0.001. But this means that it is a significant difference between 2 or more of our treatment means. And then similarly to how we write for t-test, these are our degrees of freedom, and here we have 2, right? Degrees of freedom for group and degrees of freedom for error. So F of 3 and 36 degrees of freedom is equal to our F value, and P is less than 0.001, and our effect size, this is called eta squared, and ANOVA actually gives us partial eta squared, so that's what we would report for ANOVA as our effect size. This is actually a very big effect size. And down below we show these are the means for our 4 groups. So the no therapy, their mean mobility improvement was 1.3, plus placebo got a mean improvement of 7, conventional therapy was 12.6, and new age therapy saw a mean improvement of 8.1. Then we would also want to include the plot of our means with our 90% confidence interval bars, like this, right? So this means that we're 95% confident that our true mean for this group falls somewhere in there. 95% confident our true mean for that group falls there, and so on. We're 95% confident the true mean for getting new age therapy falls somewhere within that interval.